So last time we saw that many problems have an inductive structure, but if you are not careful, then the inductive problems get repeated. So as you approach them from different bigger problems, you might find yourself solving the same problem multiple times, and we would like to avoid this wasteful recomputation. So we said that there were two techniques that would help us do this, called memoization and dynamic programming. So let's look at a concrete example and see how this works. So just to remind ourselves, we have these inductive definitions like factorial and insertion sort, where the value for the given input is defined in terms of these sub-problems, which are smaller inputs. And you can convert these into code quite easily as recursive functions. And then when you look at the structure of the inductive definition, you can identify the sub-problems, right? So you can find out that for factorial of n, you need to directly compute factorial of n minus 1, which in turn will require n minus 2 and so on. So all the problems factorial I for I smaller than n are sub-problems. Similarly, for insertion sort, we said that every segment of this list to be sorted would be a potential sub-problem. And the goal of inductive definitions is to use these sub-problems and combine their solutions effectively to get a solution for the whole problem. So let's look at another very familiar inductive definition. So we have seen factorial, but possibly the next most common inductive definition is the Fibonacci numbers. So the Fibonacci numbers are defined as follows. We start with the numbers 0 and 1. So the Fibonacci number at position 0 is 0, at position 1 is 1, and after that we keep adding. So Fibonacci of 1 is 0 plus 1 is 1, Fibonacci of 2 is 0 plus 1 is 1 again, Fibonacci of 3 is 1 plus 1 is 2 and so on. So we just keep adding the previous two numbers in the sequence. Right? So this is a very simple code for this. So if you have something which is either 0 or 1, then remember 0 returns 0, 1 returns 1. So the value is, if the argument is less than or equal to 1, that is if it's 0 or 1, then the answer you're going to return is the argument. So this is just a shortcut for two cases in one, right? So 0 is 0, 1 is 1. Otherwise, you're going to compute recursively the Fibonacci for the two smaller values, and finally we are going to return it. Now there is a reason why I have done this convoluted thing of calling this intermediate thing a value and then returning it. We could directly have written here return n and return this expression, right? But there is a reason why I have specifically in both cases stored this value to be returned in a new name called value and then returned it, which will become clear as we go along. So let's see what happens when we take this code and we actually try to evaluate a small Fibonacci number, like say Fibonacci of 5. Right? So Fibonacci of 5, because it is not the base case, will go into this case, right? So I will have to evaluate Fibonacci of 4 and Fibonacci of 3. So it will produce these two inductive sub-problems, which will be called recursively by the code. So now we will do them one by one, typically left to right. So we will first do n minus 1 and then n minus 2, right? So we will now look at this value and we will now have to evaluate it by calling this function again. So it in turn will generate two more sub-problems, right, for n minus 2 and n minus 1 for that. So 4 minus 1 and 4 minus 2. And again we will in general go to the left of the 2 and start it again. So now we will get Fibonacci of 2 and Fibonacci of 1. And then finally we will come to Fibonacci of 2 again and we will get it to Fibonacci of 1 and Fibonacci of 0. Fortunately both of these are base cases. So for both of these I will exit without having to call Fibonacci again. So I will get back the values for both of these as base cases from my Fibonacci function. And then I will be here in Fibonacci of 2. So I will compute the value of Fibonacci of 2 as 1 plus 0 is 1. So I will now get back the value of Fibonacci of 2. Now I am here, right? And I have finished Fibonacci of 2, so I have to do Fibonacci of 1 again. So I will again go into Fibonacci of 1, but then since Fibonacci of 1 is a base case, it will immediately return 1. And now from this 1 plus 1, I will get Fibonacci of 3 is 2. Now I am here for 4, right? I have done 3 and I have to do 2. So now I will go down this Fibonacci of 2 and I will again have to start computing the whole thing again. This is what we meant by saying that the same problem comes again and again and you have to be careful to avoid it. So we've already computed Fibonacci of 2, but we have forgotten that we had computed it. So we will again expand Fibonacci of 2 as 1 and 0, again realize that 1 and 0 are the base case, and again realize that Fibonacci of 2 is just 1. So now with this I have completed the evaluation of Fibonacci of 4, right? So I now know that Fibonacci of 4 is 3. So I have gone back to the original call that I made, and the first part Fibonacci of 4 has been done, but I still have to do Fibonacci of 3. Now of course I have done Fibonacci of 3 once before, but I have forgotten it, right? This is the whole problem that we are facing. So Fibonacci 3 will again expand to 2 and 1, 2 will again expand to 1 and 0, 1 and 0 will give us back the values. So I'll again get Fibonacci of 2 is 1, once again Fibonacci of 1 will return 1, so I will again compute Fibonacci of 3 is 2, and finally I will get Fibonacci of 5 is 5, right? So what we saw here is that we are basically recomputing the same thing many times. For example, we have recomputed this whole thing for Fibonacci of 3 twice, right? So you can look at this tree structure of the recursive calls and identify these identical computations, which we are doing more than once because we are actually not remembering that we have done it before. So this is true for Fibonacci of 3, but it's also true for smaller computations. For example, Fibonacci of 2, we did it 3 times, right? So in general, this will be actually exponential. If you actually write a Fibonacci function like this and you try to run it on a reasonably small input, it will be very complicated to evaluate, even for say Fibonacci of 50 or something like that. You will find it takes it will possibly not even terminate. Whereas it's quite easy for us to write off Fibonacci of 50, right? I can start by saying this is the 0th one, this is the first one, the next one is 1 plus 0, the next one is 2. So I can write off clearly the Fibonacci numbers with no effort, right? Even though I am following the same philosophy as this inductive definition, I am not using this kind of wasteful recursive thing. So what am I doing, right? So this is the point. So one way to avoid this wasteful recomputation is actually to remember, right? So we should remember that the value that we have seen before has been computed. So if we come across it a second time, we will not recompute it, but rather remember what we have said before. So we will need to keep a table of values that we have computed, right? So we keep a memory table, let's call it a memory table, which is basically all the values of Fibonacci which I have already computed once in my life. So when I have this memory table, then I can use this technique called memoization. So memo comes from, it's an old kind of English term, memo, for something which is a reminder, right? So it's not memorization, but memoization. You are creating this memo saying, this is a to do, or this is a reminder that I've already done this before. So this is our table, and this technique of looking up this table is called memoization. So the technique consists of basically every time I compute Fibonacci of n for the first time, right, by using this recursive thing, then I will store it in this table. But if I come across it a second time, right, in general, when I get Fibonacci of n as a problem to solve, I will first look at the table. I will say, in this table, is there already a value for Fibonacci of n? If there is already a value, pick it up. Don't recompute, right? Otherwise, I will make the recursive call. And with this, actually, it turns out that you will never recompute the same value twice. So Fibonacci in particular will become linear, because we know the subproblems of, say, Fibonacci of n are n minus 1, n minus 2, and so on up to 0. And if we are only going to do each of them once, then obviously the number of total calls to Fibonacci that we really use recursion on is going to be linear. So let's see how this memoization works on the same example with Fibonacci of 5. Right, so as before, we start with Fibonacci of 5, but now we have this table, right? So this table is going to be filled as and when we encounter values that we have computed. So right now, we have not computed Fibonacci of k for any k, right? So we just have an empty table. I have just put 6 boxes there, but in general, this table will grow as we go along. So we know nothing about Fibonacci of 5, right? The table is empty. So we have to call, as usual, the recursive calls 4 and 3. Now we know nothing about 4, as usual we'll do it left to right. We know nothing about 4, so again we have to make a recursive call 3 and 2. Once again we know nothing about 3, so we make a recursive call. So far we have not done anything new, right? We are just following the same trajectory that we did when we did the direct recursive call. Finally, when I do 2, I get these recursive calls 1 and 0. And now I start getting answers, right? So technically speaking, even the base case, I don't know until I reach the base case through one of these recursive computations. So now I realize that if I do it left to right, that Fibonacci of 1, the function tells me, is actually 1. So I will compute it, return the answer, but I will also put it in the table. So this is my first entry in the table. It says for k equal to 1, Fibonacci of k is 1. So remember that this table is not necessarily getting filled in the order 0, 1, 2, 3, 4. I am filling 1 first, and then because I have done it in this order, I will then find 0 and I will make an entry for 0 also. So it says now I know in my table that Fibonacci of 1 is 1 and Fibonacci of 0 is 0. This is different from saying it's the base case. The base case still means I have to evaluate and reach that point. This is saying that if somebody asks me Fibonacci of 1 without executing the function, I will look at this table and tell you it is 1, right? So now I come back and now I have got a value for Fibonacci of 2. So now I put an entry here saying the Fibonacci of 2 is 1 because I have computed it and I am never going to write this tree again. So now I go back to this call, right, and it asks me to go down and find out what is Fibonacci of 1. Now again I would like to emphasize we are not going to call the function because we are first going to look at this table, right, and we are going to say aha, Fibonacci of 1 is something that I have already seen before. So I will return 1 not because it is the base case, but so when I write it in orange now it means this function was not evaluated, it was actually looked up, right. So I first look up the table. If the table value has an entry for this argument, I will return the value from the table, otherwise I will call the function. So this version of Fibonacci of 1 did not actually reach the code for Fibonacci of 1, it just directly returned it. So now with this I have also computed Fibonacci of 3, right. So Fibonacci of 3 is now 1 plus 1, so that is 2, and this now gives me a new entry in my table saying that for k equal to 3, I know that Fibonacci of 3 is 2, right. So now I come back to the call for Fibonacci of 4 and it is going to ask me to evaluate Fibonacci of 2. Now in our earlier version we had to again expand 2, but this time I look up and I find that 2 is there. So I will look up the table and again it will become an orange evaluation, which is that it did not call the function, it just looked up the table and returned the value that the table gave, right. So you believe that you have computed it once and the value does not change. So if it was already known to be Fibonacci of 2 or already known to be 1, it is not going to change. So it is just 1, you just look it up and give it back, right. So with this now I have computed Fibonacci of 4. So I can now make a new entry in the table saying Fibonacci of 4 is 3. So now I finally come back to my original call Fibonacci of 5 and now I have to again evaluate Fibonacci of 3, but same thing. Instead of expanding this whole tree as we had done the first time, I will realize that 3 is actually an entry in my table. So I will look it up and again I will make an orange call to Fibonacci of 3 and get back the value 2 directly by just looking up this table. So this 2 came from here. And now I have 3 plus 2, so Fibonacci of 5 is a new entry in my table and I get Fibonacci of 5 is 5, right. So this is how we memoize. As and when we compute a value Fibonacci of k, we make an entry in this table. You can think of it for now, its simplest way to think of it is as a dictionary, right. With a key k, I put the value Fibonacci of k, so that the order in which the keys come does not matter. I just have to check if the k I am looking for is a key or not, right. If it is a key, then I pick up the value. If it is not a key, I make a fresh entry. So this was our original Fibonacci, right. It was just a naive recursion. It just said that if n is less than or equal to 1, then return the value as n itself, otherwise do the recursive computation. Now we have to embed this table in it, right. So we will assume that we have this dictionary called fib table, which is defined outside. So I am not going to define it inside. So it is a kind of global dictionary. Let us assume that it is available to us and it is initially empty, right. So what I will do is I will check whether the argument that I have got is a key in this table, right. And if it is a key in this table, then I will return the value of that key. If it is not a key in this table, then as before I do this computation, right. And now you can see why I did not want to return directly here, because I want to keep this value around so that I can put it into the table, right. That is the reason why we split this return n or return fib n minus 1, fib n minus 2. Instead of just directly returning it, we stored it in this intermediate value so that we can now introduce this line which says, okay, here is my dictionary, create a new entry in the dictionary for this key for which there was no entry before. Why do we know there is no entry before? Because if there had been an entry before, I would not have reached this point at all, I would have just returned, right. So we make an entry and then we return. So this is our first computation of fib table, fib of n, but the next time is going to be in the array, in the dictionary. So the next time I am not going to call this function again at this point, I am going to just return without doing the recursive computation. So this is how we would memoize our Fibonacci function. Now there is nothing very specific to the Fibonacci function, we can take any function. So supposing we have a function of 3 arguments, say f of x, y, z, right. So now if I see a particular combination x, y, z a second time, I should not compute it again. So here now my dictionary keys will be these triples x comma y comma z, right. So I will take the argument that I have got and I will say, is this triple x comma y comma z, is it already known to be a value in this dictionary? If it is, then I will just look up the table with that key, right. So here I had fib table for fib, here I have some arbitrary function f, so I just call it f table, right. So I assume that I have this empty dictionary to start with, right, which is defined outside somewhere, so I can access it globally from here. So I will now take this xyz, check if it's a key there. If it is not a key, I will recursively compute the value of f of xyz given whatever is the inductive structure of f. Right? It does not matter, this is a generic thing. Any f which has an inductive structure, there will be some way to compute it from subproblems. And then at the end of this computation, before I return the value, I will make an entry, right. This is the crucial thing. I will update my table saying, now I know the value f of xyz. So this should be, sorry, this should be f table, not f, right. So I will take and make an entry in f table saying f table with this key xyz should have the value and then I will return. So this is a very generic thing. You can take any recursive function, memoize it by just making sure you have an appropriate dictionary sitting around. So the next step from memoization is what is called dynamic programming. So in memoization, what we did was we recursively evaluated the function, and every time we came to a subproblem, for the first time we used the recursive structure, the second time we looked up the table. So we saw these subproblems in the order in which they arise. Now what dynamic programming says is that, okay, you know these subproblems are there, right, and there must be some dependency, obviously, right. So the subproblems depend on, I mean the main answer depends on the subproblem, and the is really local. So when I say, for example, that factorial of n, right, I said that it depends on factorial of n minus 1 down to factorial of 0. But the dependency is not direct. I do not need to know factorial of 0 upfront to know factorial of n. I only need to know factorial of n minus 1, right. So this is the immediate subproblem which gives the answer, but for that I will need the previous subproblem and so on. So there is a kind of dependency structure among the subproblems saying, in order to evaluate this subproblem, so Fibonacci it is n minus 1, n minus 2. If I know n minus 1 and n minus 2, I can solve n. For factorial it is n minus 1, but then n minus 1 in turn depends on n minus 2, n minus 2 in turn depends on n minus 3, and it goes all the way down to 0. So, right? So these must form a DAG. A DAG, remember, is a directed acyclic graph, right. It cannot have cycles, because if Fibonacci of n requires n minus 1 and n minus 1 requires n, then how will I proceed, right. So these have to be resolvable down to a base case, otherwise your inductive definition is not well formed. So if you have a well formed inductive definition, you should be able to unravel it down to the base case and then stop at a point where you do not have any incoming dependencies, right. So this is, remember when we did this DAG, we said that there will always be a node which has no incoming edges if it is a DAG. So these form the base case, the DAG of dependencies or subproblems. So the base case are those problems which do not have any prerequisite. So now we can go back to what we have seen before, which is you can evaluate DAGs sensibly by going from those with no prerequisites and gradually eliminating the prerequisites, right. This is the topological sort. So if you evaluate the values in topological order, then you never need to make a recursive call, because when you need that, the table has already been filled. So remember that when we did memoization, we did not anticipate. So when we did fib of 5, we had not pre-computed 4 and 3, even though it is sort of obvious that 4 and 3 were needed. We waited and then we called the recursive function for 4 and then we looked at 3 and then 2 and then 1, and then we worked backwards. Right? In dynamic programming, what you would say is, oh, I know that 0 and 1 are required for 2, I know that 1 and 2 are required for 3, so let me do it in that sequence, right? So I start with the cases which are the base cases, do not require a recursive call, so that when I come to the first case that requires a recursive call, Fibonacci of 2, I already have the base cases. Right? So if you look at this DAG structure for Fibonacci, so these are the subproblems, right? So Fibonacci of 5, I need 5, 4, 3, 2, 1, 0, and the DAG structure just says that 4 and 3 are both required for 5. Similarly, 2 and 3 are both required for 4. Similarly, 1 and 2 are both required for 3. And finally, 0 and 1 are both required for 2. And 0 and 1 themselves are base cases and I have no dependencies. So now I can enumerate this in any order. Normally, you would enumerate it in the order 0, 1, 2, 3, 4, 5. Right? But because these are both equivalent base cases, you could also do it in the order which is what we did when we did memoization, 1, 0, 2, 3, 4, 5. Right? Because up to this point there are no requirements. It's only here that I have the first requirement. So when I do 2, I had better have done 0 and 1 both. But I could have done it in either order, 1, 0 or 0, 1. right. So, normally when we do dynamic programming, what we will do is we will do it in sequence, right. So, we will say here are the cases that I can do right at the beginning, then here are the next cases that I could now that I know this. So, I can fill up that same table, that memo table that I had, I can fill it up from no prerequisites to the final answer without ever making a recursive call. So, this is dynamic programming. So, to summarize, memoization says never recompute the same problem twice. Every time you use a recursive definition to compute a value, store it in a table so that you can look up that table before you make a wasteful recursive call the second time. On the other hand, dynamic programming says the same thing, but it says we will avoid recursive calls altogether, right. We will look at the inductive structure of the problem and build in our minds or in practice, it does not really matter. Normally, it is kind of implicit, you do not actually explicitly draw the DAG I have done before, but you try to work out this dependency. What do I need for f of k, right? And then you say make sure that those are evaluated first. So, you work backwards and you say okay, which is the first thing I can evaluate, start with that and then build up this table from bottom up, right. So, this is another thing that you often hear about dynamic programming, it is bottom up. Whereas memoization is top down. You start with the problem you want to solve and you keep breaking it down into sub problems, but you never do the same problem twice. Whereas dynamic programming says anticipate all the sub problems you might need and systematically evaluate them so that when you come to a new sub problem, the previous sub problems that it needs are already evaluated and you never make the recursive call, right. So, this is memoization and dynamic programming.